class, we're going to be focused on conservation principles. You've learned about, ever since high school, conservation of energy, conservation of mass. We're going to be starting with those underpinnings and then work our way to understanding the fundamental equations that describe some of the atmospheric properties that give rise to severe thunderstorms. So let's start with, Ben, we're good? Awesome. Conservation of energy. We're going to be using the first law of thermodynamics related to the conservation of energy to effectively derive how lapse rates change with respect to time at a given point. So we're talking about conservation of energy. We are saying that when we add some amount of heat to an isolated system over some time interval, dq dt, where this is the energy added to the system, this is going to be distributed into two, or partitioned into two parts. The change in internal energy with respect to time, du dt, as well as the work done by the system. So again, change in energy will be partitioned into what's related to the change in temperature, internal energy of the system, as well as the work that's done by the system on the surrounding environment over there. And we're going to assume a nearly an adiabatic process over here, in which case dq dt is going to go to 0. That's an assumption we're going to make in terms of understanding this. We're going to remove that assumption later on. But for now, if we have the case that dq dt goes to 0, and we're dealing with an adiabatic process where there's no exchange of heat between the system and the surroundings. If we were to have the case, and I hinted at this earlier in class, we have a particle of air that's forced to rise and encounters relatively lower pressure. It expands, it does work on the environment. This particular term is positive. This is 0, and therefore this must be negative over here. So the change in temperature with respect to time is negative. They are partial cools. That's something that's no surprise from what we've learned about in earlier classes. On the other hand, if a parcel of air is forced to subside in the atmosphere, it's going to be encountering relatively higher pressure. Lower in the atmosphere, work is going to be done on the parcel. dw dt in this particular case will be negative, therefore, given the orientation of signs relative to what is doing the work. This is negative. This will be positive, such that this is 0. And we have a rise in temperatures of the parcel of air. Adiabatic warming, that's effectively what we're talking about in that particular case, with the opposite being adiabatic cooling. So that's just a statement of conservation of energy from the first law of thermodynamics. So that's no big surprise there. And what you'll be seeing in the midterm exam number 2, which you'll be getting today as a take-home exam, will be you're effectively going to be able to write this statement of the first law of thermodynamics is the enthalpy form of the first law of thermodynamics, which I'm going to write out over here. You'll be performing the derivation for this in the examination. dq dt is equal to Cp, specific heat at constant pressure, change in temperature with respect to time. And this is in Lagrangian form over here, minus alpha dp dt. Right over here, and you'll show how that goes from this later on. And we're going to call this quantity change in the energy exchange with respect to time, we're going to just call this over here Q dot. That's the change in energy with respect to time. And we're going to talk about effectively now expressing these two terms over here, dt dt and dp dt. We're going to be working with a lot of manipulations to make these effectively get this in a form where we're dealing with the vertical change in temperature with respect to height. These are written in Lagrangian form right now. We're going to want to eventually get things into an Eulerian framework. We're talking about the change in lapse rate at a fixed point in the atmosphere with respect to time. So we're going to have to be changing this or translating this into an Eulerian framework over here. So let's start out with this, what I'll call term number 1. Term number 1 over here, dt dt. Remember, dt dt, Lagrangian, can be expressed in the Eulerian framework as the rate of change of temperature with respect to time at a fixed point in the Eulerian framework, plus the horizontal advection of temperature, plus the vertical transport of temperature. That is the term number 1 over there. And then number 2, this term 2 over here, we're going to work with it by starting out with hydrostatic balance approximation, hydrostatic approximation over here. 0 is equal to minus 1 over rho dp dz. In this particular case, this is just the upward acceleration associated with decreasing pressure through the atmosphere instance that is being balanced by the downward acceleration due to gravity over here. And so let's then express this over here, bring this to the left-hand side. 1 over rho dp dz is equal to minus g. And then we're going to express 1 over rho as alpha, or specific volume. Alpha is equal to alpha dp dz is equal to minus g over here. And then in this case, if we want to deal with a dp over here, let's isolate dp. So I'll keep running this over here. Dp is equal to minus g over alpha times dz. So we've just brought dz to the other side and divided both sides by alpha. All right, so let's proceed over here. Well, we have a dp. We want a dp dt. So let's divide both sides by dt. So we'll have dp dt is equal to minus g over alpha times dz dt. That all works out relatively well over here. And so what we're going to do now is that we have equations for dp dt as well as dt dt, and we're going to plug everything in to our equation for q dot. So q dot, in this case, is going to be equal to cp times dt dt, which we have an equation for over here, right off to the side. Cp times partial t plus UH dot del HT plus W partial t partial z. So we've accounted for that term over here. And then number 2 term over there, minus alpha times dp dt. That's just going to be minus g over alpha dz dt. So minus alpha times minus g over alpha dz dt. And then let's simplify this over here. Q dot is equal to Cp times partial t plus UH dot del HT plus W partial t partial z plus, well, the alphas divide out over here. Minus signs, we get plus 1 over there. So we have g. And then remember, dz dt is just the rate of change of vertical coordinate with respect to time, which can be just equated to the vertical velocity w over here. Now, when we're talking about environmental lapse rate, we're interested in the rate of change of temperature with respect to height. And for environmental lapse rates, we're going to have a negative sign out front. That's going to be the environmental lapse rate here. The variable we use to describe environmental lapse rate is going to be gamma. But notice we have a partial t partial z. We have partial t partial z. In order to actually get something in the form of partial t partial z, especially since we have a partial t over here, we're going to take the derivative, partial derivative, of both sides with respect to z, so that we're able to deal with something on the right-hand side that involves partial t partial z. So at this point, we're going to, and I'll start writing this over here, we're going to take minus partial z of both sides to get the following of this minus partial q dot partial z is equal to Cp times partial t. And we're, yes? Okay. Second, I want to, let me see if I can tell. It's not good. All right. Does that work? Excellent, thank you. Partial t. And the idea here is when we're taking the partial derivative with respect to z minus partial t partial z, I should say, minus partial z of both sides, we want to bring the partial z inside. So remember, when we're dealing with partial derivatives, we can flip the order of differentiation. And we're going to try to construct this optimally so that we end up with partial t partial z's as we have defined with environmental lapse rate. So we'll bring the partial z inside over here to get minus partial t partial z. And then we'll proceed with the product rule, dealing with this dot product over here. We'll take the partial derivative of UH with respect to z, partial UH partial z, dot del HT. And then we have to take the remaining portion of the product rule plus UH dot del H minus partial t partial z. So again, remember we take the derivative with respect to z, minus that, times this, plus that times the derivative of this over here, where we're bringing in the derivative inside to get partial t's, partial z's. So let's proceed with this. continue over here. So plus, we'll continue with the product rule, partial W, partial Z, minus partial T, partial Z, plus W, partial Z, minus partial T, partial Z. Again, using the product rule, and we've just taken derivative of this times that, plus that times the derivative of that. And we have one last term left to deal with, in this case over here, minus G, partial W, partial Z. So when you go back through your notes, make sure that you just effectively see the trick where we're bringing in, when we're taking the derivative with respect to Z, we're bringing that inside so that we have arguments of environmental lapse rate, or gamma, throughout these equations. All right, so we're going to remind ourselves that gamma is going to be defined as minus partial T, partial Z. So we can rewrite this equation. If I write here, will you guys be able to see that or no? Yes, very good. We'll proceed. We have minus partial Q dot partial Z. And that's going to be equal to Cp times, well, we have partial T of gamma. We have a gamma here, so that worked out relatively well. Partial gamma, partial T, minus partial UH, partial Z, dot del HT, plus UH dot del H gamma, plus gamma partial W, partial Z, plus W partial gamma, partial Z, minus G partial W partial Z. So we've effectively just placed gamma in place for each of the minus partial T partial Z's. And what we're going to do is bring this term over here over to the left-hand side. And then at the same time while we do that, we'll bring the left-hand side term over to the right-hand side like that. And with that, I'm going to erase what's on this portion of the board and continue with that manipulation. All right, so we're continuing with bringing two terms on opposite sides of the equation to get the following. So we'll bring over the Cp term over here. So we have minus Cp partial gamma partial T over to the left-hand side is equal to partial Q dot partial Z, bringing that left-hand side term to the right-hand side. And then we have the remaining as follows. Minus Cp partial UH partial Z dot del HT plus Cp UH dot del H gamma plus Cp gamma partial W partial Z plus Cp W partial gamma partial Z minus G partial W partial Z. All right, so a bunch of terms over here. What we're going to do right now is divide both sides by Cp. And that's going to give us, with partial gamma, partial T is equal to minus 1 over Cp partial Q dot partial Z plus partial UH partial Z dot del HT minus UH dot del H gamma minus gamma partial W partial Z minus W partial gamma partial Z plus G over Cp partial W partial Z. All right, we're getting closer. We now have a long equation for the rate of change of environmental lapse rate with respect to time. So we're getting closer. Let's now group some terms together, starting out like this. We'll have partial gamma, partial T. So we're just going to bring terms together on the right-hand side of this equation. We'll start out with the advection term over here. So we have minus UH dot del H gamma. So we got that one covered over there. Minus W partial gamma partial Z. And that's that one over there. Plus partial UH partial Z dot del HT. That one is right over here. Minus 1 over Cp partial Q dot partial Z. And that would be this one over here. Minus gamma partial W partial Z. That's that one over here. Plus G over Cp partial W partial Z. All right. Some things may be beginning to look a little bit familiar here. Here's advection. Here's another term you may have seen before, something involving energy exchange and some other processes. Now let's make another simplification over here. When we're dealing with acceleration due to gravity divided by the specific heat at constant pressure, G over Cp, let's plug numbers in over here. We know that G, 9.80665 meters per second squared, divided by 1,004 joules per kilogram Kelvin. And remember, no need to memorize units over here. Joules, as we talked about here, form of energy, a Newton meter, force dotted with displacement, kilogram times Kelvin. We know Newton is just dealing with over here, kilogram, meter over second squared, and then we have the leftover units of meters times kilograms times Kelvin. So that's just expressing joules per kilogram Kelvin out in terms of kilograms, meters, and seconds over here. Kilograms will divide out over here. We know that the meters in the denominator over here divide out like that. And we're going to be left with, second squareds also divide out over here. So we're left with something approximately 9.8 or so, rounding these to some extent. 9.8 times 10 to the minus 3. Kelvins go upstairs over here, so we'll have kelvins. And then meters remain downstairs over here. Kelvins over meters. And let's make this simple in terms of kelvins or degrees Celsius in terms of a change of temperature. With respect to kilometer, we'll multiply this by 10 to the third meters over 1 kilometer. So we're just multiplying by 1 over here so that we're able to divide out the meters. And that leaves us with, well, 10 to the minus 3 times 10 to the 3, just 10 to the 0, which is 1, with 9.8 Kelvin or degrees Celsius per kilometer. Well, that is just the dry adiabatic lapse rate. So G over Cp can be just substituted with the dry adiabatic lapse rate over here. 9.8 degrees Celsius per kilometer. That works out great. Well, let's actually plug that particular concept in over here. We'll plug in gamma D over here and then group these two terms together to get the following: partial gamma, partial T is equal to minus UH dotted with del H gamma minus W partial gamma partial Z plus partial UH partial Z dotted with del HT minus 1 over Cp partial Q dot partial Z plus dry adiabatic lapse rate minus environmental lapse rate, that's this term over here, multiplied by the rate of change of vertical velocity with respect to height. This is the lapse rate tendency equation. Very important equation. This tells you how the environmental lapse rate will change with respect to time. Effectively, what are the physical processes that generate lapse rates, deplete lapse rates? That's all described in this equation over here. And we're going to go through each of the physical meanings of each and every one of the terms in this equation. So let's start out over here with term number 1. And I'm going to erase everything to the right of the final forms of these equations that we have over here. And again, this effectively explains how that thermodynamic sounding will be modulated over time owing to the physical forcing mechanisms on the right hand, described on the right-hand side of that equation, so that we can say something about how that lapse rate profile might adjust over time. So we don't just look at a model forecast sounding and see changes to the thermodynamic profile. We actually can look at observed soundings and see really what's going on in the real atmosphere to make some assessment about the validity of a model solution. For instance, can we trust a given model's thermal profile based on what's happening in the observed environment? There are a lot of assumptions that are made in numerical weather prediction, and so we can actually perform some validation by understanding how that temperature curve will actually vary, and particularly lapse rate changes within that profile over here. Let's look at this forcing term number 1 over here. Let's say we're dealing with synoptic scale lift, and we know at the ground We have no vertical motion, and permeability boundary condition effectively is going on at the ground. And suppose we have large-scale ascent occurring, where we have W greater than 0 within the atmosphere. In this particular case, partial W, partial Z is going to be positive. And that is the case as we have vertical motion that increases above the ground, where we have no vertical motion, such that we have stretching occurring within the large-scale environment where we have lift ongoing. All right, so if partial W, partial Z is greater than 0, typically in the standard atmosphere, the dry adiabatic lapse rate will be exceeding the actual environmental lapse rate. In other words, it's rare for this particular difference over here to be negative because the environmental lapse rate is typically less than the dry adiabatic lapse rate in the standard atmosphere. Otherwise, we tend to have a lot of things take place that we don't actually see ongoing in the true atmosphere. And we can get into some more of those details later. But going along the lines with the standard atmosphere, environmental lapse rate being less than the dry adiabatic lapse rate over here, that particular term, partial, gamma D minus gamma, partial W, partial Z, this difference over here is going to be positive for synoptic scale lift. This will be positive. So the contribution to the environmental lapse rate with respect to changes in time is going to be for an increase in lapse rate, environmental lapse rate, with respect to time owing to large-scale ascent. Well, that's pretty interesting. We've all heard of lift in the atmosphere before. When lift is happening, we actually get destabilization take place. That's pretty interesting. It's right here from the result of conservation of energy is effectively what we end up with over here. Well, how does that really manifest itself physically? How does conservation of energy have something to say about that destabilization process? Well, we know that with height above the ground, if we have strengthening vertical motion, we know that cooling is going to be greater than near the ground where we have less vertical motion. So more vertical motion, more cooling going on adiabatically aloft, compared to near the surface where vertical motion is minimal owing to impermeability. And so we have more drop-off in temperatures with respect to time aloft than down below, and therefore the lapse rate profile must steepen. So that effectively over here is adiabatic effects, where we have greater cooling aloft associated with ascent than down below because of stretching of the column. In other words, differential vertical motion through the vertical depth of the atmosphere resulting in a differential cooling rate with height above the ground. So that's adiabatic effects over there. Then term, we'll say 2 over here. We'll call this 2. These are diabatic effects over here. Effectively changes in the lapse rate profile associated with vertical variability in diabatic processes. For example, vertical variability in latent heating due to condensation, for instance, is going to result in changes with respect to time in the lapse rate owing to the vertical variability in heating rate, for instance, through diabatic processes. So this is adiabatic processes. These are diabatic processes over here. Let's look at these two terms over here. Well, this is horizontal advection of lapse rate. That's pretty interesting. Temperature is advected. We've all heard of warm advection, cold advection. Well, not only is temperature advected, lapse rates are advected. We actually can take lapse rates, finite layer vertical changes in temperature, and push them around effectively, not only horizontally, but also vertically. So this is effectively advection and vertical transport of lapse rate, or moving lapse rates along and the flow. And that's something that if you've seen before, you've heard of the elevated mixed layer before, where we have relatively arid portions, higher terrain, western plateau. We get the development of a deep boundary layer over relatively drier ground out west, over the mountains. Solar energy is much more likely to be absorbed by the ground in that area with a limited low-level moisture, limited vegetation. We get very deep boundary layers fostered out west, and then those steep lapse rates associated with the deep boundary layer out west are then advected out over, returning low-level moisture over the Great Plains, allowing the same lapse rate profile aloft out west to appear over the Great Plains in an elevated sense. So effectively, that deep boundary layer out west is carried eastward by this term over here. This term explains the elevated mixed layer, where we have a deep boundary layer, steep lapse rates that are pushed along. And in cases where convection erupts over the Great Plains, for instance, those lapse rates are processed. We effectively have reduction in lapse rates, and it's harder for severe weather to experience the same lapse rate profiles and robustness out east, because that Great Plains, I should say, that Western Plateau environment is effectively processed before it gets all the way, say, to the East Coast. It's effectively used up or processed convectively over the Great Plains before it gets out to the east. Now, in some scenarios where we have steep lapse rates that are generated over the Western Plateau, they're advected eastward across parts of the Great Plains, and convection fails to develop for any number of reasons over the Great Plains, that steep lapse rate plume can extend all the way to the east, and that's how we get some of the more robust severe weather events across the southeast U.S., parts of the eastern United States, because this is operating efficiently and hasn't been depleted by convective processing over the Great Plains. So these are very important terms in terms of the EML perspective, and they come right from conservation of energy. So all these phrases that you've learned before, elevated mixed layer and steep lapse rates aloft, and the implication for the robust nature of convection, all is from conservation of energy, which is really interesting, since we're able to connect all of these principles of meteorology to the basic underpinnings. And we only have one term left. We'll call this set of terms 3. We'll have term 4 over here. This is partial UH, partial Z, dotted with del HT. One thing in general, I am very much a stickler for vector analysis and appropriate use of vector notation. So make sure, we'll talk more about this as we head into latter parts of class, that you take care of dot products and cross products. So we're dealing with partial UH, partial Z, dot del HT. Effectively a change in the horizontal velocity or with respect to height or the vertical shear of the horizontal wind, dotted with the temperature gradient. So we're just looking effectively at the component of the vertical shear in the direction, or dotted with the horizontal temperature gradient, or vice versa, since we're taking a dot product and we're not dividing out by anything else over here. So say, for instance, in terms of term number 4 over here, we have a temperature profile, or I should say not a profile, but rather a horizontal plan view depiction of temperature with warming going towards the east, 5 degrees Celsius, 10 degrees Celsius, 15 degrees Celsius. These are just isotherms. And say that we have a westerly wind superimposed on that temperature gradient, something like this, where we have increasing winds with height above the ground, increasing westerly winds with height above the ground, and increasing temperatures as we go towards the east. In this particular case, the del HT is going to be pointed toward the warmer air over here, going up the slope effectively in the temperatures. And we're going to assume again that we have background westerly winds over here that are increasing with height to give us westerly wind shear, partial UH, partial Z. So in this particular case, mathematically, partial UH, partial Z, dotted with del HT. In this case, these vectors over here are parallel to each other, and therefore the cosine of the angle between them, which is 0 degrees, is positive 1. And so this product, dot product over here, is going to be positive, and the contribution to lapse rates is going to be partial gamma, partial T, is going to be greater than 0. So we have vertical shear that has a component along the horizontal temperature gradient. In this case, we end up steepening the lapse rates. But what does that mean physically? This is cold advection. We have flow that's going across isotherms towards warmer air. Well, if we have vertical shear such that the westerly flow increases with height, we have more cold advection going on with height than down below. And therefore, we'll have more cooling take place aloft than down below, and we'll steepen the lapse rates, which is just the change in temperature with respect to height. In this case, what we call that physically is differential temperature advection, where we have a change in temperature advection with respect to height, yielding a change in the lapse rate profile with respect to time. So we have differential thermal advection going on over there. We have lapse rate advection over here, which is going to have some implication on differential advection in general when we have steep lapse rate plumes extend over rich Gulf moisture, for instance, diabatic effects and adiabatic effects. All right, very good. Let's continue. So that's conservation of energy, lapse rate tendency equation. And we're going to go relatively quickly now through implications of conservation of mass. and the effective statements that we can come up with for large-scale meteorology and large-scale vertical motion using the notion of conservation of mass. So